In the second part of chapter 29, we're going to look at the physics of molecules. And when you take atoms and you combine them into molecules, you get more energy states. And it turns out the energy states tend to cluster in bands. And so I can get some different properties. Now we're going to look at the spectrum of some molecules, not the emission spectrum like we looked at with the hydrogen and the helium. We're going to look at the absorption spectrum. So right here, I have a filter, and this is a theater gel. This is a gel that you use to make colors in the theater, and white light comes in, and what gets transmitted is magenta. But let's look at the spectrum of what happens when the filter is working its magic. So now, we've got the white light source here. You have the rainbow, all the colors which are being emitted by that white light source. But if I put the magenta filter in front of the bulb, what you can see is this. It blocks out part of the rainbow. And it's taken out a swath in the middle of the spectrum. It kind of wipes out the green. So what you see is magenta. The light that comes through is magenta, but that's because it's absorbed the green and a little bit of the blue. So this is the absorption spectrum of the particular molecules inside this filter. And we also have a cyan filter, and a cyan filter absorbs the reds, and a yellow filter absorbs the blues. Now think about this. The yellow filter absorbs the blues. The cyan filter absorbs the reds. When I combine the two filters, what's left over is green. So a mix of cyan plus yellow gives green. Now, there's other properties we're going to look at with molecules in chapter 29. When you have molecular spectra, you can also have a phenomenon known as fluorescence. And this is something you've seen before. There's certain things that glow under what are called black lights. Now, black light is just an ultraviolet light. But you can get fluorescence even if you're still in the visible light spectrum. This laser pointer is violet. And if I look at the light from it, you can see what color it is. It's violet. It's just at the edge of the visible light spectrum. But if I shine it on fluorescent objects, the color of the light that comes in, violet, is different than the color of the light that comes out. So violet light shines on this red bouncy ball, and the light that comes out is red. And so it's a different color that comes out. Now here's a question for you. Which photon has higher energy? The photons that are coming in from the laser pointer, or the photons that are emitted by the ball? The absorbed or the emitted photons? Which has a higher energy? We'll give you some choices. Well, you know violet is short wavelength. Given the formula that we have for photon energies, high photon energies. The red light is near the other end of the visible light spectrum, long wavelengths. Given the equation that we have for photon energies, low photon energy. So the energy of the photon that comes in is greater than the energy of the photon that comes out. And we show in the book that there's an internal transfer of energy. Energy is still conserved, but some of the photon energy that comes in is subsequently lost. It's a lower energy transition that leads to the emission of a lower energy photon. And that leads to the phenomenon of fluorescence. So if I have things that are fluorescent, and I shine ultraviolet light on them, they emit light, and the color of light that they emit is different than the color of the light that comes in. And then, in chapter 30, we're going to consider things like this cup, because this cup, in addition to being fluorescent, is also radioactive. There are atoms inside here which actually fall apart. The nucleus of the atom falls apart. How that happens and why that happens is something we'll consider in the next chapter.